Cutting EEG is launching the cutting hubs everywhere around the world for 2022, 3, and so on. We need to organize locally, independently. The idea here is really not that Cutting EEG is going to spread around the world, but rather sprout everywhere. I really wish that we can do this together. Instead of cutting hubs, we talked about it earlier, I would like to call this cutting gardens, vegetable gardens, in which we plant seeds and grow food locally while thinking globally. This is really my best hope at the moment for this. This is 2020. We are in Marseille. We were all together live. Please, guys, come and let's give a little kiss to everyone. Keep at it. Stay close. And see you very soon.
Where I come from? See me them a dancing now. Young feelings. Corbina.
And we are back. We did it. We have managed to create what promises to be the greatest event. What an adventure, let me tell you. I recall planning this with the first online meeting a year ago with people from all around the world. We've seen many or few already logged in. We have 21 gardens. Let me listen to them all, list them for you all. We have people in Belgrade, Serbia. I don't hear you. We have 3 gardens in the UK, one in Bournemouth, one in London, one in Dundee, 3 gardens in Germany, Frankfurt, Münster, Regensburg, one in Genova, Italy, one in Ghent, Belgium, Haifa, Israel. We have all heard about the tragic events in Israel, and we know that this region is under a great deal of tension at the moment. Haifa gardeners, I know that your university is closed. I hope that at least some of you are able to hear us. We send you our thoughts, and we hope that the situation improves soon and hope to see you the next time in person. We also have gardens in La Havana in Cuba, Los Angeles, USA, Tehran in Iran, Montreal in Canada, Nijmegen in the Netherlands, Oro Verde in Argentina, San Sebastian in Spain, 2 gardens in Chile, in Santiago and Talca, 2 gardens in France, in Caen, and last but not least, in Lyon. Lyon, can I hear you? Yes, I do. We have an amazing program. What will happen right here on Crowdcast? It will include 40 different sessions online, talks, tutorials, and workshops, and many more that will happen just locally everywhere. This all would not be possible without the amazing networks of gardeners who have managed to organize all these sessions. That's already a great amount of work, and I would like to hear you.
And you don't hear me anymore. Well, that's a risk of live broadcasting. My mic just shut down right in the middle of the intro speech as I was going to ask for a round of applause for all local organizers. Okay, let's pause that video for a second. What I wanted to say then was that many of the local tutorials that were happening that week had been made possible thanks to a dedicated training generously offered by 4 Toolbox Masters in the name of Britta Wessner, Robert Ostenfeld, Arnaud Delorme, and Olaf Demigen. Thank you all again for your precious advice and your time. Okay, now back to the original video when my dear Anne-Sophie Dubarry rescued the live session and moved on.
So, our first speaker, without waiting too long now, our first speaker, Catherine Tallon-Baudry, is an internationally renowned researcher for her pioneer work on oscillations. Catherine is a CNRS research director at the Laboratoire Neurosciences Cognitives et Computationnelles at ENS in Paris, where she's leading the team Subjectivity, Brain, and Visceral. And today we are lucky to have Catherine presenting her work on gut-brain consciousness axis. Thank you again, Catherine, for being with us. I'm going to leave the stage to you for the next 20 minutes, and you can now start sharing your slides. Thank you, Catherine.
Okay, if I don't see any message saying that you can't hear me, I'll just proceed. So thanks a lot, Anne-Sophie, for this kind introduction. It's an honor to be invited. And I'd like to thank all the bright and dedicated people who are making this novel type of event possible. You are clearly designing the future. So congrats to all, and don't pay too much attention if there is any small glitch in the process. So I'll start to begin my talk by reminding everyone of the standard paradigm in cognitive neuroscience. And in this paradigm, the brain extracts information from the external world, processes this information, and then acts back upon the world. This paradigm has been extremely successful in the past 20, 30 years, and we've learned really a lot. And I would like just to expand slightly this paradigm by considering the body. In the standard paradigm, the body is not really useful except to act on the world. And the point I want to make today is that there is actually a whole world inside, as rich and complex as the external world. And how the brain monitors this internal world is called interoception, which is essentially perceiving bodily variables. It, of course, has a feedback action on the state of the body, but I will mostly focus on this ascending part. And why is this important? Well, clearly, regulating the physiological state is the most basic thing a brain can do and should do, because this is what is required to maintain the organism alive. So interoception is clearly a driving force both for evolution and for behavior. But there is a bit of a paradox in the literature, in the sense that the cognitive brain, the one that interacts with the external world, is somewhat separated from the housekeeping brain that is mostly subcortical. And today, I won't talk so much about the regulation of the physiological state itself, but rather try to show that interrogating internal bodily state is a process which is so important that it has become a kind of default routine for brain processing. So this occurs at all times. It's most often unconscious. Apologies. And this happens even in the absence of homeostatic challenge. So during all your favorite cognitive tasks, there is usually no homeostatic challenge. And I want to convince you that a lot is going on regarding interoception. And finally, to conclude that cognitive and interoceptive functions are tightly integrated. So I want to focus my talk on two parts. One is, if indeed the brain is constantly interrogating bodily internal state, then this should have an impact on spontaneous brain dynamics. And to show you that this interoceptive routine has cognitive relevance, in particular for subjective cognition. This I will do in the second part of my talk. And I will focus mostly on two organs, the heart, that you're probably all familiar with, that the heart is beating, it's generating its own electrical activity, generating contractions, and something similar is happening in the stomach, which will be the other organ I'll be discussing. And essentially, the idea is fairly simple, is to think, okay, now we have oscillators in the body that are actually coupled with a complex system, which is the brain. So what happens in terms of brain dynamics? So let me first say a few words about the gastric slow rhythm that you might not be familiar with. So the stomach is essentially this pouch that fills during digestion, contracts, and expels food downwards. I'll be mostly talking about what happens outside digestion, and our participants were recording during fasting, moderate fasting. So this is a section of the stomach wall with the two muscular layers. And in between, there is a specific cell type called interstitial cells of Cajal, which are not neurons, but they have neuron-like properties. And in particular, they generate their own electrical activity at all times. And they make contact with the smooth muscles and training their contraction during digestion. And they also make synapse-like contact with vagal sensory neurons. So potentially this information is relayed up to the brain. And in humans, it's fairly easy to record the activity of the stomach by placing electrodes on the abdomen. And here is a typical raw signal you can get, where you can see this slow gastric cycle. So one cycle is about 20 seconds. Superimposed on it, you have the faster respiratory cycles, about 4 or 5 seconds. And each of these vertical ticks is actually a heartbeat, a cardiac contraction. And what is nice with the stomach is that it has a very sharp signature in the frequency domain. The rhythm is fairly regular, though not absolutely regular, but fairly regular. So we asked a simple question: can we consider the stomach as an electrical pacemaker constraining spontaneous brain activity? And because I like to be provocative, I will start by sharing some results from fMRI, although this is an MEG, EEG meeting, but I'll explain you why. So we recorded both the EEG and the bolt signal in participants at rest, but then we treated the bolt signal as electrophysiologists would do, which is why I dare to share fMRI results with you. So essentially, if we schematize the gastric rhythm in blue here, okay, so we have this fairly regular rhythm, sometimes a bit faster, sometimes a bit slower, and we search for brain voxels whose time series are phase-locked to the gastric rhythm. Okay, so it can be with a short phase delay or with a longer phase delay, but what matters is that it closely follows the gastric rhythm. And when we look at this phase synchrony between the stomach and the bolt, we find that there is quite a large number of brain regions which are coupled more than one could expect by chance. So this is what we call the gastric network. It explains, the gastric phase explains about 15% of bolt variance in those voxels, so that's quite large. And it's organized as a sequence which cuts across resting state networks. So it begins in somatomotor regions and ends in visual cortices. And because I'm an electrophysiologist at heart, of course, we also did it with EEG. And here we looked for phase amplitude coupling. So if we now have the EEG like this, we looked at phase amplitude coupling for all brain signals in gray, varying from 1 to 100 hertz. And we found convincing evidence for coupling with the alpha rhythm, originating in the regions generating alpha. Okay, and we found that gastric phase explains about 8% of alpha variance. So again, it's not explaining everything in terms of alpha fluctuations, but it's also not negligible. Before I get to the question, we have Bayesian evidence for an absence of link with state anxiety in the young healthy participants we analyzed, and that was during resting state. There was no particular we did not generate anxiety. And I want to emphasize the fact that we find gastric brain coupling in sensory and motor regions. So we find somatomotor regions, auditory regions, visual regions, and if we put a region of interest in the olfactory cortex, we also find coupling there, which honestly came as a surprise. This was not what we had predicted. But we are not the only one to find that. So first, the gastric network was also observed in rats, and they obtained results very similar to our findings in humans with coupling in sensory regions. And if we dive into the older literature, including in humans, for instance, experiments where participants had to ingest an inflatable balloon, for instance, then it was commonly reported, for instance, that there was reactivity in visual cortices. So we don't know what is the meaning of this, but I hope it opens new horizons into how to think about spontaneous brain activity. I now switch to the second part of my talk, which is about the cognitive relevance of those signals outside homeostatic challenges. So the reason why I was interested in this is that how the brain is monitoring bodily variables might be a way to build a subject of experience. So why would we need to build a subject of experience? So this goes to questions about what consciousness is and how it relates to cognition. So there are usually two aspects in consciousness. One, which is that when we are conscious, there is no doubt that we have better skills and abilities. Okay, we are better at logical reasoning, at orienting our attention, at planning, at expressing things verbally, etc., etc. But there is one fundamental aspect about conscious mental life, is that it's made of experience. It's just what we experience at any time. It can be, exhilarating, it can be completely neutral, but this is what conscious mental life is made of. And subjective experiences do require a subject of experience. And one of the questions to better understand consciousness then becomes, how can we build a subject of experience in the brain? And there is a long tradition of associating bodily signals with some form of self. So first, because they are internal and private, so in a way they are self-specifying for the brain, but also because they refer to the basic form of self that needs to be protected, fed, or regulated. And here there is a form of magic trick, as very often in consciousness research, which is it might be that the very notion of subject of experience is derived from this very basic form of self related to the organism itself. In this view, consciousness would be generated in the brain, but it would be a property of the whole organism. Okay, like an isolated brain in a vat would not be conscious. And the reason why to focus on the heart and GI tract is that those are life-sustaining systems, constantly feeding the brain with inputs, but also varying at the timescale of perception and cognition. And if we try to analyze what are the properties of subjective experience, there are three important properties. First, any subjective experience feels unified, although we know that in the brain it's encoded as a collection of different information. It's experienced in first-person perspective, so with a certain point of view on the outside world, and it has what the philosopher Dan Zahavi called intrinsic mindness, the fact that it's your experience. You don't even have to think about it. Whenever you experience something, it's your experience, except if you have psychiatric pathologies. And in this view, the idea is that maybe the fact that the visceral organs are monitored in exteroceptive sensory areas is actually useful to bind together information from the external senses by creating correspondences between different frame of references, where typically you have a gaze-centered frame of reference for vision, and you have a skin organized reference frame for touch, and putting the two together is not necessarily that easy, but if you have the same signals shared in those two reference frames, then it might become easier. So that's the overall hypothesis, and in this hypothesis, I would like to emphasize that it's not necessary that there is a change in bodily state, because whatever happens, the heart is beating and the gastric rhythm is being generated, and there's no need to consciously perceive visceral signals. So that's a kind of a grand hypothesis that we don't prove fully at the moment. But how can we tackle this experimentally? So we look at heartbeat evoked responses. So of course, in this audience, you all know what a visual evoked response is. Present a visual stimulus, record noisy EEG or MEG data, repeat the process, average, you get a transient. One can do the same thing by locking the data to the electrocardiogram, so the R peak or the T wave, and getting a transient that is called the heartbeat evoked response that was first described in the lab of Chandry in the 80s. This is how it looks, for instance, in our own data in somatosensory cortex, where we get a very nice transient response when we lock the data to the R peak of the electrocardiogram. When it comes to scalp data, it's slightly more complicated, as most of you are familiar. We also record the electrocardiogram with electrodes or with squids in MEG. And so we get a cardiac artifact, which is essentially reflecting the electrocardiogram. So there are all kinds of tricks to attenuate this and making sure that we are not actually analyzing the electrocardiogram with fancy methods. So in my group, we had a whole program to test whether heartbeat evoked responses would co-vary with subjectivity in a large number of cognitive domains. And I, of course, don't have the time to present them all, but I just want to show you 2 examples and maybe encourage you then to look at the larger literature on heartbeat-evoked responses. So the first example I want to give is about the self, where we actually designed an interrupted thought paradigm where participants had to fixate for quite long intervals. So they got bored and started mind wandering. And from time to time, we interrupted what they were thinking about. And we asked them to rate how much they were engaged as a person in their thoughts. So they were trained to do that because it's not necessarily that easy. And then we looked at heartbeat-evoked responses during the thought they had been rated. And we splitted them by high or low engagement of the self. And what we found is that in regions of the default network, posterior cingulate cortex and ventromedial prefrontal cortex, there was a difference in how the brain was responding to heartbeats, with larger responses for high self. Because this was one of our early experiments, we were quite happy to see that we could confirm those results using intracranial EEG. So we had 2 patients, one with an electrode in PCC and another one with an electrode in VMPFC. Of course, we were not lucky enough to have one patient with electrodes in both regions. And I'll just show you the results for those 2 electrodes in VMPFC, so for the local intracranial EEG between those 2 contacts here. Where here we can look at the heartbeat-evoked amplitudes on a trial-by-trial basis, against the ratings of the self that were given by the patient. And you can see that even in a single patient on a trial-by-trial basis, we get a pretty good correlation. Okay, and the second example I want to give you is about consciousness state this time. So here, in collaboration with the Coma Science Group in Liège, and in particular with the work of Jitka Annan and Stephen Lores, we analyzed patients who have been emerging from coma from some time, but they emerge from coma with disorders of consciousness. And the question is whether they are conscious or not, which is a very difficult clinical diagnosis. And in Liège, they base a clinical diagnosis on 2 things: signs of intentional behavior. Like if you ask the patient to squeeze your hand and he does squeeze your hand, then clearly the patient is conscious, or at least has moments of consciousness. But these behavioral scales might easily miss, more subtle aspects of consciousness, or simply if the patient is paralyzed, there's no way he can display signs of intentional behavior. So they also base a clinical diagnosis on a measure of glucose metabolism obtained with PET emission tomography in Liège. And at the moment where they acquire the PET data, they also record resting state EEG, which is what we analyzed. And so what we did, we first had a set of patients with a clinical diagnosis. We looked at heartbeat-evoked responses, and we trained a classifier to reproduce the clinical diagnosis. And then we had a test set where we predicted a clinical diagnosis, compared it with what Liège had found, and we had an 87% accuracy, which is not bad, but it's not the main point. The main point is that if we redo the whole procedure, but this time we take random EEG segments, so same amount of data, same length of segments, same number of segments, but randomly positioned with respect to heartbeats. Whatever we do, so we repeated the whole process, including the training, etc., we always get a lower accuracy. So what those data mean is that responses to heartbeats do convey some specific information on consciousness state. Okay. So across all those experiments, I won't present more here, but we do have experimental evidence in favor of a link between heartbeat-evoked responses and subjectivity. We, of course, have all kinds of controls to show that it's specific to heartbeat-evoked responses, etc., etc. We don't know yet, for instance, on experiments where we present stimuli on screen and we find that heartbeat-evoked responses have a link with subjective reports. We don't know what is the mechanism of interaction between external or cognitive activity with heartbeat evoked responses. This is something we are working on now. So we can't prove this idea that actually visceral monitoring might provide some binding operation between different reference frames that could explain the core properties of subjective experience. So this does still remain as an hypothesis at the moment. Also, I would say we have first evidence that it might make sense to pursue in this direction. Okay, so I hope that I have at least convinced you that interoception is actually tightly intertwined with how the brain is processing information from the external world, and that the interaction between interoception, perception, and cognition makes a lot of sense to be analyzed in the future. And I will finish by thanking members of my team who went along with me along this quite risky path, at least mostly at the beginning. It was really a risky research, so thanks a lot to all of them. Thanks to the developers of the toolboxes we are using to analyze the data, including fMRI data, I must say. And if ever someone is interested in this position, then be in touch. Thank you all for your attention.
We're super happy because we have plenty of questions and interesting questions coming from our gardens. And unfortunately, we won't be able to address them all. But let me start with the first one that came several times and that was upvoted several times. It's about the causal directionality of the signals. So I think the question is whether you have a hint on what's driving in between brain and gut. And
yes. That's a very important point. So for the cardiac signal, I guess it's fairly clear that we do have a response after each heartbeat. And there might be other signals that actually drive change in heart rate, for instance. The two might be related at some point, but here we clearly have a transient after each heartbeat. Okay, so for this response, I guess we have at least a fairly clear starting point that we first get a response from the brain to an input. For the stomach, it's a bit more complicated. Because we do have something which is more oscillatory in nature. So we don't have a full answer to what is driving what. Still with, so in fMRI, we don't know. And with electrophysiological tool, we use transfer entropy to assess directionality. So it's a measure of directionality, which is worth whatever it's worth. But this measure of directionality was, at least for the alpha rhythm, was clearly that gastric phase was constraining the amplitude of the alpha rhythm much more than the other way around. So that's what we have in terms of evidence. Then there are also those experiments where there is a mechanical stimulation of the stomach. Where, for instance, they also found that there that this resulted in changes in activity in the visual cortex, for instance. Okay, so everything we are seeing might not be purely ascending, and in any case, if we have something which is a loop, there are points where it's difficult to disentangle what is ascending and descending. But at least for part of the story, we clearly have evidence for ascending signals.
Okay. Thank you very much. So I'm going to take a second question here. What is the impact on cognitive research?
Okay, that's a big question. So, as I've said in my talk, I think in cognitive research there is a bit of a paradox. On the one hand, we have everything, for instance, about decision making and reward. It's in humans, at least, it's about about choosing the game that will give you the highest reward, and it's supposed to be derived from mechanisms, from ancient mechanisms, where you are searching for the right source of food, for instance, so things which are related to interoception. So there is, on the one hand, this recognition that there is this drive and that there is this evolutionary history that high-level human cognition is derived from more ancient mechanism. But when you look at the literature, actually, there is a big gap. Like there is this, what I call the clever stuff done by the cortex, and then everything that has to do with interoception is mostly confined to brainstem structures and things that are more like reflex. And I think that what we are showing is that the two are actually much more intertwined. So whether the impact is going to be massive or small, that does not depend only on me, but I think we are hitting on this paradox in cognitive neuroscience. Giving at least some flesh to the notion that, yes, interoceptive mechanisms are a driving force.
Okay, well, thank you very much. So I may have time for a third question. And so, yeah, what is the role of, sorry about that, the role of blood flow on this whole process? This is a question from Frankfurt.
Thanks a lot, at the Garden Frankfurt, for raising it. So for the stomach, we don't necessarily know, but for the heart, there is a possibility that actually it's a pulsation of the blood in small vessels, which is detected. So first, let me give you the conventional view, is that the heartbeat evoked response is driven by mechanoreceptors in the aortic arch and in the carotid sinus, okay, and relayed through the vagus and glossopharyngeal nerve. This is certainly part of the story, but there is another part of the story which is very likely, which is that it might be that both astrocytes and neurons directly detect the pulse of the blood in vessels within the brain, which then, of course, becomes a completely different story. So there is little evidence for this yet. There is one line of research in vitro showing that astrocytes can transduce change in blood pressure and induce firing in both pyramidal cells and interneurons. And there is another line of research which is not yet published, but the preprint is out. Very exciting work by Veronika Egger in Germany, showing both in vitro and in vivo that neurons actually transduce the pulse, and probably through piezo receptors.
Okay, thank you very much. I think we're probably going to thank you again, Catherine, and go to the next speaker. So right now you're staying with us for the discussion afterwards, and thank you again. See you at 4, I believe. Right. Hello, Freek. Can you hear me? While you're adjusting the microphone, I may introduce you. Can you hear me now?
Yeah, we can hear you.
Okay, fantastic. Hi, Freek. Thank you very much for being with us today. So our second speaker of the day is Freek van Ede. And Freek is the head of Proactive Brain Lab in Amsterdam. He is right now presenting from CuttingGardens in Belgium. And today he will present his work on focusing working memory for action. So thank you, Freek. I'll leave you the stage for 20 minutes, and you can start sharing your slide now.
Okay. Yeah, thanks so much for organizing this. It's a really great initiative that we're here in this garden, but there are so many gardens across the world where presumably there's a very similar setup. I'm glad I chose Ghent because we're in a very sunny garden at the moment. I hope this is the same for the other gardens, but of course I don't know. So yeah, I guess like Catherine, I'm gonna make a case that we should really study cognition and brain activity, not in isolation, but like in her case, in the context of bodily signals, in my case, in the context of action or in the context of behavior. And so I want to focus on some of our EEG studies, EEG insights into the mechanisms by which we use working memory to guide adaptive, appropriate behavior. Now, given we're in the theoretical advances session, I thought I'll start with the big question, which is, what does the brain actually do? Of course, a bit silly, but the point is that often in psychology, we kind of have this kind of a model that the brain is organized kind of in modules that do perception, or and then perhaps cognition, and perhaps finally action, right? And so this is from the work of Paul Sisek, which has done some beautiful writings on it, and I can recommend you have a look if you don't know about this paper. Because he suggests that maybe there's an alternative way of thinking about brain organization that is much more focused on the perspective of action coming first. And so the idea here is that the brain might be organized in modules that have to deal with specifying relevant parameters of actions and selecting among them. And as part of that framework, things like attention and working memory, etc., are there to subserve these behavioral goals. And so you could think about it as action not being the end point, the final thing you do in a trial, but actually the starting point, right? The reason that you're invoking cognitive processes such as attention and working memory in the first place. And if that's true, then there are kind of two implications, among others, which is that we shouldn't study cognition, cognitive processes in isolation of action, right? And maybe that we cannot even do so, even if we attempt to do so. And so I just want to kind of share some results of some of our research that can really fit this the second way of thinking about the brain. And so I organized my talk according to these two kind of implications here. So chapter one is we shouldn't. And so I'm going to make the case for our research that deals with the visual working memory. And so it's useful to ask, why is it that we keep things in working memory in the first place? And so if I'm the soccer player, right, I might currently be looking at the ball because that's my target. I want to shoot ball. But I'm going to hold relevant information in my visual working memory. And I'm going to hold that information in mind because I want to guide my appropriate action, right? I'm going to hold like information about where the goalie is located and in which part of the goal he is in order to guide appropriate behavior, which is to kick the ball. Here's just another example. If I drive by a road sign with directions, I need to keep that information in mind somehow, and not because I want to keep that in mind because I like how it looks, but I want to keep that in mind because I need to make the appropriate action. In this case, to take the correct exit, right? Okay, and so given these kind of examples, we then really also need to study visual working memory in the context of behavior and anticipated behavior. And so for us, that means we shouldn't focus so much or not only on like how is it that we store information in working memory, which is also a relevant question, but the question that's been driving our research is how is it that we prepare and utilize whatever is in memory for guiding these anticipated actions? Okay. Now, that's kind of a kind of sketch where we're coming from. And so now perhaps it's time to dive into some EEG studies. So the first EEG study that we ran in this kind of line of studies that I'm going to be showing you is here. And this is a very simple task that we developed where participants are just asked to keep in mind two visual representations, which are two visual objects, which are two different bars, in this case of different color and different orientation, in order to later reproduce the orientation of one of these pieces of memory when one of them becomes probed. So in this particular case, when the dial appears, it indicates that the yellow item that you're holding at that moment in your working memory is supposed to reproduce from memory. So you reproduce the orientation. Okay. Now, what we did in this task is that if we would probe you after a short working memory delay, be more likely to be asked about the yellow item. But if we would probe you after a long working memory delay, you'd be more likely to be probed about the blue item. Now, if we think about working memory from this kind of metaphor of a thinker who is reflecting on the past, then there shouldn't be any difference here between these two conditions, because from the outset of the trial, you just have to encode these two pieces of information and wait for one of them to become probed. But the idea is that if we move away from this metaphor of a thinker and think of working memory much more as an actor who's kind of using its memory to prepare for the future, then we would expect a difference. In the sense that this actor should be more ready to kind of guide their behavior by the yellow representation early, but by the blue representation late. And so that's exactly what we found evidence for in the behavioral data. So if we probed the memory content early, participants were significantly faster to start their behavior for the item that they expected to be probed early than for the item that they expected to be probed late. But if the same item that they expected to be probed late would be probed late, they were much better at this again. So we really saw evidence for this kind of reprioritization as a function of as time passes. But then, you know, this is just behavioral data. So then you can ask, is this just because participants expect the probe to look at a certain color, and so when it doesn't match the color, they somehow slow down? So this has nothing to do with actually people shifting their attention around among the memory contents, or is it really what we're interested in, kind of participants dynamically refocusing different representations of the whole in mind in anticipation, in anticipation of which representation they're going to be needing? And so fortunately, EEG was to the rescue here, because what we found, at least in this later interval, was a lateralization of EEG activity, this particular case in the alpha band, according to the memorized location of the memory item that they're focusing on, despite the fact that the task and everything happened centrally. So the fact that the EEG lateralized suggests to us that their attention was shifting among the memory contents. And so EEG was here really helpful for us to kind of track this internal reprioritization of internal visual representations in working memory. Okay, so we then reasoned that if visual working memory is for action, then shouldn't we also investigate these visual representations and their selection in contexts where they are actually associated with different actions? And so we made a very simple but effective tweak to our laboratory task, where this time we linked the tilt of the bar directly to the action that was necessary to reproduce the orientation. So the way this works is that at the end of the trial, participants can press one of two buttons, a button with the left hand and with the right hand, and then they have to press the button which starts tilting the dial towards the right or towards the left. And so they just have to press the button until they hit the orientation that they want to report, and then they let go of the button. And so in this particular case, we would cue the participants to retrieve the orange item from memory. And because the orange item is tilted towards the right, they would have to press the button with their right hand, start tilting the dial until they hit the exact orientation that they have in their memory, and then they finish their report. Okay? Now, critically, what we did here is we independently varied whether they would have to select the left or the right memory item, and whether that memory item was associated with the left or right action or response hand. And you can kind of see this here. So, yeah, I guess it's clear. You select either the left or the right action, the left or the right visual item, but that item could be left or right tilted. And so if it was left tilted, you would end up requiring your left response hand. If it was right tilted, you would end up requiring your right response hand. And critically, because these two factors are orthogonal in our design, an equal number of trials are in each for these cases, this enables us to independently track in the EEG signal signatures of visual selection and signatures of action selection. Okay. So then we envision two scenarios. First is if we imagine that during the memory delay, participants exclusively engaging in visual working memory, then after they get the cue to select one of the visual representations in memory, they would have to do the visual selection. And once they've selected the relevant item, they would have to think what they're going to do with this item. And so then they would engage in action selection, right? And this kind of model that I was sketching where you do perception, cognition, and finally you do action. But alternatively, perhaps what happens here is that during the memory delay, participants are not only holding these two visual representations in mind, but they're also preparing for the two potential actions that are associated with these visual representations. And so if that's true, then upon the selection queue, they should be able to simultaneously access not only the relevant visual representation, but also the relevant action plan and select these things concurrently. Okay, so here's the data. Here's time after the queue on the x-axis, and on the y-axis is a classification of whether that trial was associated with the left or right visual stimulus and or with the left or right action. And so first of all, we can clearly decode from the EEG signal from around 200 milliseconds after the color change the fixation cross, whether participants are selecting in their mind the memory representation that used to be on the left or used to be on the right and encoding. And we refer to this as the visual selection, right? And so now the question is, if we train another classifier, which is orthogonal by our design, to distinguish whether participants are selecting a response with the left or the right response hand, is that going to be following a series, or is this going to happen in parallel? And so here's the data. We find clear evidence for concurrent selection of both the visual representation and the associated response hand, and that goes with this visual representation. And now it's not the case that our classifier is somehow picking up the same information twice, because when we did a searchlight analysis, we saw that the visual information really originates from the back of the head, whereas the sensory motor, kind of the action plan information, really localized to the sensory motor cortices. Okay, so I think here we have like EEG providing key evidence that visual working memory retention of multiple items and planning of multiple potential actions are often studied in kind of separate fields, but really are working hand in hand here during this period of memory-guided behavior. Okay. So then we asked, having shown that the items are action ready at the time of the probe, right? What I just showed you. We next asked, when is it that these action plans form over the course of the working memory delay? And so one possibility is sketched here, which is that kind of as the delay passes, you kind of gradually get more ready to make your to guide your behavior. And to look at this, well, we made a very simple tweak to our laboratory task, which was we presented the queue before the stimuli appeared. So now you have a pre-queue, so you know that the orange item is the one you're going to need at the end of the trial. You haven't seen it yet, and then upon encoding, you can select the orange item, but you can't yet act on it because you still need to go through the working memory delay, and eventually you get the go signal that you can go. And so, rather than this kind of gradual buildup of the readiness that I just sketched, what we found is that immediately upon encoding the sensory information, participants would prospect kind of the action, the manual action that would go with this visual information, even though they're not executing this action at this point. And this kind of fades away again, and then ultimately they get ready to really make this action, right? And so what the EEG reveals here is that kind of participants plan the output of what they're having in working memory, what they're going to do with this information. They plan this immediately at this kind of input stage. We could even show that kind of when we split the trials by how fast or slow people ended up being after the 6-second working memory delay, we saw that they had significantly stronger action encoding, as we refer to that, in trials where they end up being faster 6 seconds later. Yeah. Okay, so that's the end of chapter 1. So in studying how working memory serves behavior, which has been kind of one of the questions that we're trying to address, EEG has been very instrumental to us to reveal how internal representations are dynamically prioritized and reprioritized at relevant moments, how action plans are brought into working memory immediately upon sensory encoding, and how visual representations and kind of parallel action plans kind of are really be stored together in working memory such that they can be selected concurrently. And so it's really showing how action planning and visual working memory, although they're often studied in kind of separate camps by different people, are really working hand in hand here to afford effective memory-guided behavior. So I hope to have some time to keep going with chapter 2 here. Yeah? Okay, good. So I just argue that we should maybe study things like visual cognition, visual working memory in isolation of action. But here I can go a step bolder and say maybe we also can't, right? And I want to talk specifically about microsaccades. So microsaccades are very small miniature eye movements that we make even when we attempt to keep fixation. And so, many times in our experiments, we put up a fixation cross just to control where people are looking. But in reality, what happens is something like this. This is slowed down a little bit from reality, but you can see here that while the eye is trying to keep fixation on the fixation target, there's actually occasionally the kind of very small saccades being made, which are these microsaccades. Now, we can then ask, okay, should we as MEG researchers be bothered by this? And the answer is, well, maybe we should, because we did something very, very simple. We detected these kind of microsaccades as they occur in a signal while we also were recording EEG. We aligned the data to the moment of the microsaccades, and then we just separate trials where the microsaccades were made to the left or made to the right. Okay? When we do this, then locked to the microsaccade, we see kind of very prominent transient lateralization of EEG alpha activity that has a kind of spectral profile and a topography very similar to the type of alpha modulations you might see during kind of covert shifts of attention or spatial working memory. And so here EEG helps us to kind of reveal this kind of transient action locked brain activity. But the question then is, may this actually account for cognitive EEG modulations? So, and as it happens in this particular task, when we give this cue that prompts people to select something from their memory, we see very clear lateralization of alpha activity in line with the fact that they're deploying their spatial attention to the appropriate memory item. But we also see, this is a separate talk if I had more time, but in short, what we also see is a systematic bias in microsaccades by the direction of the focused memory item. So there's significantly more microsaccades that occur towards the focused memory item than away from it. And this effect is completely driven by saccades below 1 degree visual angle, as you can see in that heat map over there. And so the kind of elephant in the room, or micro-elephant in the room, if you will, is whether these spatial biases in microsaccades may account for spatial biases in EEG activity when we're shifting around covert attention. And so as it happens, we were able to look at this because we had both of these signals in the same task. And so what we did here is we sorted the trials from 2 to 600 milliseconds. You can see that's the window where we have more towards saccades than away saccades. And we sorted the trials as being a towards saccade trial, an away saccade trial, or a no saccade trial. Okay, and it's all based on this 2 to 600 millisecond window that we identify in the top plot here. And then we can, of course, after we've made this trial separation, we can now look at our EEG data, see whether the alpha lateralization that we observed is any different between these 3 trial classes. And so here's the toward microsaccade trials. We get this beautiful alpha lateralization. Here's the away microsaccade trials, and you can see that the direction of the microsaccade matters for the kind of clarity of the EEG signal. And when you overlay them, you can see indeed in the away saccade trials the effect is perhaps a bit delayed and also attenuated. Now, we can also show that the latency matters. So the microsaccade that is made towards the focused memory item could be made early after the cue or later after the cue. And we split the trials by a median split. And there's some overlap at the group level, but at the single subject level, this is a perfect median split of early and late. And then we can look at the alpha lateralization in these trials. And again, you can see that there's a correlation here. So in the early microsaccade trials, the alpha lateralization also happens earlier. And in the late microsaccade trials, the alpha lateralization also happens later, right? So they're also correlated in latency. But so despite the fact that they are correlated, when you make a microsaccade, its kind of direction and its latency is correlated with the EEG signal of covert shifts of attention. But critically, you don't always make a microsaccade. And so here's maybe the key insight. When you don't make this microsaccade, you have perfectly preserved alpha lateralization, at least in our task, right? And so suggesting that while the microsaccades and the EEG modulations might be correlated, maybe because they are 2 reflections of the same process, which is shifting your attention, is not that one is necessarily causing the other. Okay, so the summary of the second chapter is that microsaccades don't just add noise, right? They're small and maybe they're a bit scattered in direction, but they are systematically modulated by experimental conditions, which is interesting for us because it implies action circuitry in the brain in cognition. But for the purpose of this talk, they're systematically modulated and they're associated with canonical EEG modulation, such as the alpha layerization. But that doesn't necessarily mean that alpha modulations, as an example, are necessarily driven by these microsaccades. Okay, so if I just zoom out a little bit and try to get to some overall take-home messages, I guess I try to show that cognitive functions such as visual working memory, as an example here, and action might seem quite remote at first, but actually quite interdependent in reality. That the temporal dynamics that we get from EEG are really kind of central to unlocking these interdependencies. So I show, for example, how you dynamically reprioritize memory contents in service of expected behavior, how you hold visual memories and action plans available concurrently. You can select them concurrently by the kind of simultaneous time courses of the visual motor selection, how you encode the prospective action immediately upon sensory encoding, and how you get like transient EEG modulations locked to actions. And I guess as a final point, I think it's really also important, careful experimental design, orthogonalizing your variables, for example, to allow it to independently track them, has been really key to some of these insights here. And also a careful analysis, such as action-based trial sorting, like sorting the EEG signal based on the microsaccades, for example, enabled to study cognition and action in kind of more integrative manner. So bringing action into your task could be a good thing, but you also want to still be able to track the cognitive processes. And so it really comes down to careful experimental design and careful analysis, I think. So with that, I'd like to thank my team in Amsterdam, my collaborators at the University of Oxford, where I spent 5 years as a postdoc, and a lot of these studies were done still back there. And of course, the funding and all of you. So, thank you.
Okay, so we have many questions from all over the world, around the world, and so the first question was, what is is coming from Frankfurt and Lyon? What is the role of microsaccades exactly, and what's the link to visual modality, or could it be found also as a super model?
Yeah, I mean, well, that's a big question, and we've been using microsaccade as a tool to track internal selective attention effect, and then, like I said, that's a whole different talk that I could have given, but we're not so much studying the specific functional role of microsaccade in vision, which other people study, people like Mikhail Rucci or Rolf Engbert and Reinhold Kliegel and people. So for us, they are a readout of what's happening inside the brain's oculomotor system. So the brain's oculomotor system controls our eyes, but also controls covert attention. There's plenty of evidence for that from also recordings in frontal eye fields and superior colliculus, inactivation studies, etc. And we're showing, by looking at a peripheral readout of that the oculomotor system also contributes to shifting around attention inside the visual spatial layout of working memory. So that's all I kind of can and want to say, I guess, about like the potential role. So for us, it serves as a tool, really. Yeah. Okay, so we also have a question from Caen and Donostia. They ask if you could comment more about the individual variability in the saccades. Oh, the question is about the saccades. Okay, that's fine. Sorry about that. Yeah. So, yeah, I have a slide on that actually, but it's you know, with these saccades, it's quite easy not to see them because we have plots showing that, hey, people keep perfect fixation is fine. But once you know how it looks, how you can characterize it, you can actually see that in the individual level. You could every individual basically show their microsaccade bias by shifting around covert attention inside working memory. It looks a little bit different in different people in the sense that the saccades are a bit bigger or smaller, a bit earlier or later. But basically, it's a very reliable effect. Yeah. We haven't really studied individual differences as such, like, you know, in a sample of 200 people with different personality traits and all of that. It would be quite interesting to do, but we haven't gotten around to that yet. So. Okay. Thank you very much. We have a question from Cuba. How could you explain impulsive behavior in the context of your results? Explain what behavior, sorry?
Impulsive.
Impulsive?
Mm-hmm.
Well, I don't know, really. Yeah, really, I don't know. It's it's an interesting question. Because impulsive, I guess sometimes you act too early without knowing all the relevant, like, visual information that you need to make that action or something. You decide too early or something. Again, it might be interesting to study this kind of like tasks that we developed to study visual selection and action selection from working memory in the context of personality kind of differences, where people are more impulsive, less impulsive. Do they show different patterns? Are impulsive people actually faster to initiate the memory-guided action, but maybe less accurate because they go too fast or something? Yeah, it'll be interesting to do, but again, we haven't done that.
Okay, thank you very much. A question from Frankfurt. What does alpha rhythm mean in this context? What is the circuit being activated that sustain the relationship between motor and perception-related activity?
So in the task I showed with the visual selection and the action selection happening concurrently from the EEG signal, I showed you the decoding results, but you also get indeed this clear alpha lateralization in the visual kind of posterior sides. And in the sensory motor sides, you get the alpha plus beta lateralization, as often reported when you do action preparation. The role of the visual alpha modulation, I would say, is somehow to do with spatial orienting, but in our case, spatial orienting inside the mind. So it's like you keep the memory representations, you kind of individuate them in memory by relying on space, right? You don't have to. We don't ask you where the item was, and it's no longer there, so you don't have to. But it seems like people remember the spatial location as a kind of scaffold to organize their memories. And then when we're asking them to select one memory as opposed to the other memory content, we see a lateralization of alpha activity consistent with orienting your attention inside your memory to the appropriate memory content. And the same for the action. I mean, you have multiple action plans that you might need to select among, and then you select the correct one, and you get the kind of canonical signature of shifting a spatial tension or shifting kind of or selecting an action. Yeah.
Okay. I'm going to take a last question, and this comes from Dundee. How might cognitive load influence the simultaneity of memory and action representation? So what might happen in an NBAC task?
Yeah, NBAC task, I don't know, but we've done the experiment with 4 items. If I had more time than 20 minutes, I would have maybe shown it, but I was very tempted to show that as well. It's actually quite interesting. When you make it 4 items, and then you can potentially, there was a reasoning plan for, keep 4. You can keep 4 items in visual working memory, but can you also keep kind of 4 action plans in parallel with them, and then you would still get concurrent selection. But actually with 4 items, we get that the visual selection doesn't care whether you're selecting among 2 or 4 items. So that's kind of a load independent. But the action selection is substantially later when you have more items in working memory. And that's interesting to us because it suggests that working memory load doesn't make it harder to access the relevant memory content, but it makes it harder to prepare for guiding your behavior based on those memory contents. So that we're writing up that paper. So hopefully, Dundee, you said, or somewhere, hopefully that's coming out soon, and people will find it at the time. So,
thank you very much. I think we're gonna take a break now. We're having a 10 minutes break. I'm sorry, 15 minutes break. Thank you again, Freek. Thank you very much.
Okay, thank you.
Okay, we're live. Everything goes smoothly, as you can see. We're going on the last but not least speaker of this session, Clément Francois. Clément is a CNRS research associate leading the LSD team, Language and Speech Dynamics, at LPL in Aix-en-Provence. And he will present us his work on the emergence of language during early development. Very happy to have you here, Clément. Thank you.
Thank you, Anne-Sophie, for this very nice introduction. I'm very happy to be here. And I would like first to, instead of waiting to the last slide, to thank the CuttingEG family, because all these guys are doing amazing things. And yeah, I'm very happy and proud to be part of it. Of course, I want to thank my funding agencies, or well, the funding agencies, without whom nothing would be possible behind the scene. Okay, so why is it theoretically important for cognitive neuroscience to study the emergence of language? Well, first of all, I would like to bring you back to a quote from, well, some statements that Nicholas Tinbergen, the Nobel Prize in Medicine in 1973, brought on the table. And that is, so he was an ethologist and he was studying mating behaviors in birds. And actually, he proposed four questions, among whom one has to do with the development. And so basically, he states that to understand complex behaviors, such as language, one must understand how it develops. So the ontogeny, the ontogenic approach allows to understand a bit better complex behavior, such as language. So this is the first statement. Studying the emergence of language is important to understand how complex behaviors in the brain and in humans are implemented. However, studying infants is kind of a challenge, as some of you may know, probably not the youngest. Babies cannot talk. They cannot follow instructions. They used to have short attention span. They have a limited behavioral repertoire, so you cannot ask them to press a button response. And those little creatures grow fast and develop extremely rapidly. So basically, different tasks must be used at different ages. And actually, EEG could be a good candidate, or could be the problem solver, as you know that we can collect implicit measures of brain functioning in quite similar situations and independently of the attentional stage or developmental stage. I invite you to look at this paper from Hervé and collaborators in the special issue of CuttingEG Neuroimage that is trying to deal with these things. So of course, even though EEG is a perfect tool to study the early development of language, there are plenty of methods from day-long auditory recordings. So basically you put like tiny microphones, tiny devices in some infants adapted clothes, and you can record spontaneous language production from the infants, but also you can disentangle or trying to define the role of parental input in the development of language skills. But this is nothing to do with EEG. You can also develop nice tricks to gather behavioral measures, such as on the left, the non-nutritive sucking procedure that is used with very young infants. And basically you can extract the amplitude and the frequency of this sucking behavior thanks to connected pacifiers. And this has been thrilling methods showing that like babies can have like very mature speech sound processing. There is also the head turn preference procedure that is a common method to study, for instance, preference or familiarity in infants, but also, of course, neurophysiological measures such as MEEG and years. Okay, language acquisition is a big challenge. We may think that babies acquire the language without effort, but actually it's not the case. The segmentation problem. Babies are not exposed to isolated words, and usually parents utter sentences, and this is basically running speech. And so the idea is that babies must segment a continuous stream of words to extract the meaning of these words. So a big hello to people in Donostia. This is Basque language. Hello, guys. Another big problem for these babies is that once they have extracted these words, they must achieve the word-to-world mapping problem and trying to disentangle what is the referent of the word form ball. Is it this picture on the left, in the middle, or on the right? And so this is a so-called word-to-world mapping. And so I'm going to try to illustrate some findings with respect to these two big problems, or which are like kind of the basics of language acquisition and learning, and that allow children to enter and to crack the code of language and to enter into this linguistic world. Basically, statistical learning could be considered as a core mechanism for language acquisition, statistics. If you look at this sentence and with the waveform of where are the silences between words, what you see and what you can clearly get is that the silences are not in phase with the word boundaries. And so this is a challenge for babies with this example. You directly get the point of speech segmentation. And actually statistical learning, so the statistics that structure the speech stream allow for this kind of computation, for this kind of problem solving. So usually this is an example that should be correctly appearing, that is not. If you hear the sentence pretty baby, the idea that the syllable pre is highly predictive of the syllable t, and you can hear this pretty sequence in many different contexts. Pretty babies, pretty faces, pretty boys, pretty girls, pretty cars, whatever. And the idea is that the transitional probabilities coming from Bayes' theorem are very high for the syllables that are within the words, while the transitional probabilities that are spanning word boundaries are decreasing, are pretty low. And so based on the extraction of this parameter, by computing the transitional probabilities between syllables, you can extract the two words pretty baby and consider them as isolated words. So this is a kind of learning mechanism that has been studied largely in the literature, and indeed the ability to isolate words from fluent speech largely rely on statistical learning mechanism. Of course, there are other cues for word segmentation, but one that is kind of universal is the computation of these kind of probabilities. And then also, this mechanism is also at play when one has to learn the syntactic rules. So for instance, when in English, when you have the is and then the verb as the ing ending, it's a kind of long distance dependencies that we have to learn to master English. And so this is also reflected in the computation of long distance dependencies. but also in terms of word reference association. So the word mapping, word-to-word mapping, is also supported by this kind of statistics. The Gavagai problem from Quine, a very famous linguist, shows that different instances of a word will occur in different contexts, and it's based on the regularities that one may manage to associate Gavagai to what is referring to. And basically, it's an implicit learning mechanism. So the idea that participants enrolled in this kind of statistical learning, speech segmentation tasks are not instructed to learn. And so even though they are not intending to learn, they manage to extract these kind of probabilities and statistics through passive exposure. These learning mechanisms is also at play in different modalities and species, showing that it's kind of a domain general learning mechanism, and that has some long life evolution through species. Okay, so the idea of ontogenic approach is to define or to decipher, to describe the developmental trajectories of specific computations or specific cognitive functions, such as speech segmentation or word-to-word mapping. And of course, one hypothesis is that this would follow a decreasing developmental trajectory with some skills that would be present in newborns or very young infants, and that would show a decrease with age. Another possibility is that it's the other way around. So the ability may increase and may be better, become better with age. And the third, but not least, possibility is that this kind of computation or cognitive function remains stable across development. So I'm going to try to show you some examples of previous studies from my own group and from other groups, showing that actually this kind of speech segmentation based on statistical learning is a stable learning mechanism through development. And okay, so it was based on our discussions with the CuttingGardens team. The idea was to try to be cutting edge, and to be I don't know what to say, to be cutting. And so, yeah, this kind of studies, of course, used behavioral measures, used ERPs, but recent developments of EEG or data analysis with EEG data has to do with neural entrainment, which is a basic property of the brain that actually refers to the phenomenon during which when you apply a visual stimulation, for instance, a flickering visual stimulus, you see the brain oscillations in phase and aligning with the stimulation. So this kind of phenomenon of neural entrainment was first interpreted as reflecting kind of a bottom-up process. So an external oscillator entrains the brain oscillators, and the brain aligns with this external oscillator. But more recently, in the auditory modality, Sylvie Nozaradan studied the processing of rhythm processing in the auditory modality, and made a very clever experimental design in which he exposed participants 3 times to the very same sequence of isochronous sounds, so which is represented here. So we have some beep, 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 that has a very specific frequency of 2.4 hertz. And when looking at the EEG, well, they saw that indeed the brain was oscillating and was showing this clear peak at the frequency of stimulation. But cleverly enough, in the second and third condition, she asked the participants to imagine a kind of binary meter or ternary meter. So even though they were exposed and stimulated with the very same frequency, those guys were thinking that it was containing a kind of march or waltz rhythm, beep pop beep pop beep pop beep or beep beep pop beep beep pop beep beep pop beep beep pop. And so just by thinking about that, by imagining the EEG while they were exposed to these continuous streams and thinking about binary meter or ternary meter, the EEG was showing exactly the peaks at the frequencies of these binary meter or ternary meter on top of this basic syllable frequency, beat frequency. So actually neural entrainment, and so it was called frequency tagging analysis, can also be used to decipher tap-down processes. This was one of the first illustration that a neural entrainment can show also tap-down processes. And this is basically the idea that we're going to try to use to dig in the speech segmentation problem. Once you exposed participants with a continuous stream of syllables, at some point, if there are some regularities, if there are some additional, more complex relationships, then the EEG should show those higher order relationships. And so just to give you a flavor of the purest data that we can get, this was done by my previous PhD student, Neus Ramos. So she did some frequency tagging with epileptic patients. So they had some intracranial recordings performed before surgery, and she basically performed the kind of classic tasks that are used to study speech segmentation. So those patients were implanted with a large bunch of electrodes, intracranial, very good signal-to-noise ratio, very good signal, were exposed implicitly, so without instructions to learn, to this 2 minutes or 3 minutes continuous stream. And as you can see, you have some colors. So this was it's a speech stream made up of 4 pseudo words, 3-syllabic words. And so you expect the brain to react at the frequency of the syllables. That was 3.3. Maybe at the 2-syllable at some point when they kind of managed to group the syllables by groups of 2, and the word frequency if they managed to segment. So the idea that if they segment and if they compute the statistical relationships existing in between syllables, then we should see a peak at this frequency. Afterwards, she performed the behavioral tasks to evaluate whether they were able to recognize those words as a proxy of learning. So these are the locations of the electrodes in those 7 patients. We analyzed only hippocampus and electrodes in the auditory regions. And what she saw is that actually the auditory electrodes, so all those electrodes that were implanted in the auditory cortex were showing this clear peak at the syllable frequency and showing very little response at the word frequency. And it was the other way around for hippocampal electrodes. So auditory regions highly respond to syllable frequency, and hippocampus responds mostly to word frequency. This was just to give you a primer of the figures that I'm going to systematically show with those peaks at the frequency of the syllable and at the words. She also performed, conducted a very nice study using frequency tagging with a multimodal experiment with 9-year-old children. So basically, these 69-year-old children were exposed to auditory stream in which we superimposed and presented regular pictures of objects that were supposed to be associated with the auditory words, and of course tested the different conditions, the word recognition and the word picture association.
those 9-year-old children performed quite well in the speech segmentation and the association task. So it was a clear evidence showing that these children were able to perform both tasks at the same time. But of course, she was also recording EEG. And what she saw, so she had a learning and a random condition to get a baseline. And what she saw is that over frontal region, over frontal electrodes, there was a clear peak at the syllable frequency and at word frequency that was higher for the structure stream, the one that is containing the statistical cues with respect to the random one. And of course, over occipital regions, this peak was bigger and higher for word frequency because the words, the objects were presented at this specific rate. So it was like confirming like previous studies in adults using EEG and ERP analysis, but it was a first glimpse into this frequency tagging method. She also performed some connectivity measures in the sensor space using WPLI to avoid these effects of diffusion. And what she saw is that over in between frontal and occipital electrodes, there was a high connectivity at the syllable frequency, and that was indeed higher for structured versus random streams. So this was the first evidence that 9-year-old children can perform speech segmentation and meaning mapping concurrently. And this data was showing that neuron entrainment at both syllable and word frequencies, which was some kind of information to infer that top-down modulation or the consistent association between visual and auditory modalities can induce a facilitation of learning. Okay, let's dig in more into the baby stuff. A first study, 2 minutes, perfect. It works, and it works. I'm done. Okay, so this was another study from Ghislaine Dehaene groups by Claire Capdebon, trying to learn the long distance dependencies. And actually what they use is the ITC intertrial coherence to show that those babies, 8-month-old babies, were indeed showing those peaks at the syllable and word frequencies. So actually 8-month-old infants can show significant entrainment at syllable and word frequency, and that non-adjacent dependencies are already computed at this age. And finally, a very last results from Ghislaine Dehaene group with the paper of Flo in 2022. She performed basically the same. Instead of evaluating the computation of long distance dependencies, it was more basic speech segmentation. And what they saw, they recorded EEG during resting state, during random presentation of sequences, and during structure sequences. And what they show is that as compared to both conditions, resting and random, the structure stream was showing this clear peak at the syllable frequency and a kind of a peak at the word frequency. So after 2 minutes of exposure, sleeping newborns can indeed show neural entrainment at word rate. So to conclude, speech segmentation via statistical learning seems to be already present at birth and appears stable across development, so which brings to theoretical insights and can inform our theoretical models of speech processing. Frequency tagging might be definitely a powerful tool to study the development of high-level cognition, and neural entrainment is a good candidate. I thank you all.
All right. Thank you again, Clément. So we're having plenty of questions for you.
Cool.
I'm going to start with a question from Dundee, both Dundee and CuttingGardens. And this is how can we be sure this is actually an entrainment and not just evoked responses?
Yeah, that's the question.
Do you hear me? Well, yes?
Yes, we can.
Yes, that's a very good question indeed. When we look at the power only, we cannot disentangle that. But when we look at the ITC, it seems that is evoked indeed. But there are some studies from intracranial patients or intracranial EEG showing that when you stop the stimulation, actually the oscillation goes on. So this is kind of an indirect evidence showing that it's entrainment and not only evoked, even though once you kick in an oscillator, it might take time for this oscillator to attenuate. So I cannot be sure in my statement saying that this is neural entrainment. But yeah, that's a big question, and actually I don't have a clear answer. I have a glimpse of answer with this intracranial data.
Okay, thank you.
Very nice question. Thank you, CuttingGardens Online Ambassador.
I have a question from Nijmegen Garden. So why is there a 2-syllable peak? If we expect peaks that are linguistically meaningful, why are we also seeing a linguistically meaningless bisyllabic peak?
Well, thank you for this nice question, Nijmegen. I would not say that a 2-syllable peak is linguistically meaningless. If you think about the associative learning mechanism that is governing this kind of computations, one may expect that at first the 2 syllables are grouped together before grouping 3 syllables. So depending probably on the level of learning, one may visualize this kind of peaks at 2-syllable frequencies. So this is the kind of answer that I would probably give. It might reflect an incomplete learning state showing this 2-syllable peak frequency.
Okay, thank you. We have a question from Bournemouth. Is there any difference between children bilingual learning and monolingual learning, where the children in this study that you presented are learning their native language or a new one?
Okay, that's a very interesting question and intriguing one that we are about to start trying to answer with a new PhD starting now. And we're going to compare frequency tagging or speech segmentation based frequency tagging in bilingual and monolingual infants. The data showed you from Neus Ramos in children was performed in Catalonia. So basically, children there are bilinguals. And of course, with these kind of studies, we try to use the phonemes that are used in the native language. So we have not done this kind of study using non-native sequences of speech sounds, and I don't know about it. So if you know, please give it to me, give me this information. I would be glad. But yeah, that would be my answer. I would expect that there are some differences between bilingual and monolingual learning children, and that's something that we're going to tackle.
Thank you. So I'm going to take a last one from Oro Verde. Did you test whether frequency tagging works with non-stationary speech patterns?
I did not. But you can use alternative methods like MTRF to study these kind of things that can deal with non-stationary speech patterns or natural speech, basically. And you can include some regresses in the analysis to check on whether this kind of peaks at word boundaries or at the frequency of those words can emerge. But of course, frequency tagging is
like a perfect fit for very regular isochronous rhythmic patterns. Yes.
Thank you very much, Clément. Okay, and thank you again for this nice talk and answering my questions, our questions, the questions coming from all over the world. Now I think we're going to take another 10 minutes to let everybody, every garden brainstorm and come up with a question, this time for our three speakers, Catherine, Freek, and Clément, all together for this session about the advances, the theoretical advances in cognition made with EEG and MEG.
Okay, see you in 10.
Yes, we're going to take two minutes to remove the questions in the Q&A that were for Clément, and then we're going to be ready to collect the questions for the general discussion.
Right.
Thank you very much. We'll see you in 10 minutes.
Okay. See you in 10.
Coming back here, I am coming back, and I'm hopefully Clément, Catherine, and Freek are coming back on stage to join me for this first end of day discussion. Hey, hi Freek, thanks. Hi Clément. Hello Catherine. Okay. Thank you very much. So we collected the questions coming from the gardens. And I'd like to start the discussion. We're still collecting the questions, so I'd like to start with one of myself. I'd like to hear your insights about the hypothesis testing or data-driven are two very different approaches. And do you think they can lead to similarly growth theories, or are they doing this in a different manner? Do one or the other can lead to faster lead to theories? Would you, Catherine, start, or I don't know if any of you wants to start.
Okay, I can get the ball rolling. That's a tough question, but I'm a firm believer that data have a lot to say by themselves. I mean, we usually run an experiment for good reason, but sometimes the data tell a completely different story. And I know that these days with pre-registration and everything, this is not popular, but I still think that exploring the data and doing it properly, meaning controlling for the fact that you test several hypotheses, but doing exploratory analysis is also super fruitful if you have good quality data to start with. But as electrophysiologists, we know that good quality data are of paramount importance.
Yes, thank you very much. Do Clément or Freek wants to jump on this, or?
I just want to say that I agree with Catherine. In fact, some of the stuff I showed you was not hypothesis driven at all. Like the discovery of this microcyclic bias was initially kind of a problem for our analysis, right? We say, there's this eye movement confound, and so we kind of something we just stumbled on in the data analysis. But then it turned to be so robust that even though we didn't pre-register or anything, it's just a super robust pattern that now we ended up using as a tool in our research. And it's totally data-driven in that sense, right? Yeah. So I agree. I think with Catherine.
Yes, I fully agree, and I think both approaches can be at some point complementary and can join or can converge. So, yeah, definitely both approaches can be valid and can be extremely fruitful if you have good quality data.
Yes. Well, do you think data-driven can be constrained a little bit by hypothesis testing? Sometimes we start to explore the data, but exploring is sometimes people are running to go to the statistics, and so sometimes we do not spend the time we should on exploring the data, and sometimes I question myself sometimes whether I have the right to explore these in terms of statistics, and what to what extent can I explore the data without biasing and being able to perform a hypothesis testing study.
If I may jump on this one, something which happened regularly in my group is that we observed some things in a data set that was not necessarily intended for this. And said, that's interesting, intriguing, surprising. And then we acquired a new data set to test the hypothesis that this was really a robust finding. Of course, in the papers, we don't necessarily report the initial incidental observation, but I think it's a good way to make sure that you're not just selecting whichever finding you find nice in your data, but you go for something which is robust and which is likely to replicate in different data sets.
Okay, well, thank you. Yeah, Clément?
No, well, go on, keep on. I fully agree, and I was just saying that I wanted to say that, for instance, in some of the projects we're currently running, we collect those auditory day-long recordings, and we have like 15,000 or more than 15,000 hours of recordings. So we have some hypotheses on some components of the role of the input that the parents can have on the development of EEG features or brain processing. But at some point, we may find some things that we were not expecting. So this will then fall into the data-driven part. So yeah, definitely probably the similar process as Catherine.
Thank you very much. Okay, I'm going to take a question from Bournemouth, which is actually the most popular right now. So for our speaker, do you have any recommendations about how your work may have clinical or other practical applications? Freek, do you want to start? Or do you have something you want to share with us about this?
Yeah, sure. So,
thank you.
So I mean, my research at the moment is not targeted at clinical insight. It's targeted at fundamental understanding of how work memory, attention, action planning, etc., work together to guide behavior. But of course, in the process, we also develop interesting ways to track across time the dynamics of attention, for example. And so that might have particular ramifications for down the line understanding particular disorders of attention, such as in ADHD, for example. Yeah, so the microscope tool I was talking about briefly is one example where we haven't applied it, or we haven't tested it in a sample of, let's say, ADHD population, but that would be quite interesting to do because it's a temporally resolved measure, and so we can measure whether there's a problem with, a delayed allocation of attention, or is inability to sustain attention, or the spatial specificity of attention is more diffuse, etc. So it's potentially a very rich measure that might have clinical kind of diagnostic, perhaps, or try to understand clinical diagnoses or the etiology of certain disorders in a better way. But again, we haven't done that yet, so I can only speculate at this point. Yeah, but thank you. It's a good question.
Thank you. Clément, would you like to share with us if you have clinical or other practical applications with your work?
Well, yeah, I have some studies, current studies running, but if I come back to the questions, any recommendations? I don't. I don't have recommendation. Do your best and do the more robust as you can do.
as you know, if you want to get into the clinical world, you need to have an assessment of the validity of your task, and this must be 99.9% of success in identifying diverging trajectories or deficits or whatsoever. I never reached this point, so I cannot give you any recommendation. But at the same time, pathological models can be very informative for theoretical and fundamental aspects. So I'm running some studies with preterms, and this can be very informative of what is the role of nature versus nurture in developing good language skills and good language abilities. So this might be a kind of a two ways travel from clinic and fundamental, but I don't have any recommendations.
Thank you.
I can jump in because I had time to think a little bit this time as to what I could say. In terms of recommendation, I think it's important to know what makes you tick and where is your intrinsic motivation. I mean, I'm in principle interested into clinical and practical applications, but this is not my main motivation. I just want to understand. So I do run some collaborations, which are very successful because my clinical partners are highly motivated to get into the clinical world and that we can really work together. The second thing is that what we do is usually pretty demanding in terms of programming, etc., and this is very often something our clinical partners don't really appreciate. So it's important to make sure that if you go for a clinical collaboration, that this aspect of the work is recognized as such and is carried out by someone who has the time and the training.
So now we have two similar questions from Lyon, both Lyon and Frankfurt. They're wondering to what extent theoretical reasoning is constrained by methodological limitations, or how do methods inform your choice of designs? We hear your insights on this. And feel free to jump in.
If I may, I think the methods don't really inform the question, but I have like a long list of questions that I don't know how to tackle because I don't have the right design. And when it comes to the design itself, of course, the methods are really important, but for the questions themselves, I'm not so sure. But it's more among the many questions one might have, selecting those we can answer now because we have the tools to answer them is important. Yeah.
Do you think it can bias somehow your design to because you have those methods and you master them? Do you think it could bias somehow the way you design the experiment, or you choose to?
I could not use the word bias because it sounds a bit negative, but I think it makes sense to
influence,
to choose a design that can answer your questions, and the design includes the methods available. So, yeah.
Can I jump in here? So, yes, two things spring to mind in my case. One is that, of course, especially EEG, MEG community, we're very focused on cortex, right? And in general, perhaps in cognitive neuroscience. And the subcortex, obviously, is very important, not only for brain function in general, but also for cognition, right? And we have undervalued systematically, I think, the role of the subcortex in cognitive processes, including intention. Yeah, for example, the superior colliculus is a small structure somewhere deep in the brain, but as these eye movement biases that I was talking about are showing, it somehow participates in this internal focusing on things that we're keeping in memory, because otherwise we wouldn't find these microsaccade biases, right? And so we don't know exactly the role, but somehow it's participating in that attentional focusing inside memory, which sounds like a very cognitive thing that we're doing. And actually it's recruiting this to kind of a deep oculomotor brain circuitry that we wouldn't necessarily measure with EEG, but fortunately we can get a little bit of a readout from other measures, such as the eye movements that I showed. And the other thing is that often we're studying kind of cognitive processes and brain activity in kind of static observers, right? And if it's all about action, we should also be studying these things in moving and kind of acting agents. And so recently, for example, just to give an example, we've been using virtual reality as another way to display our tasks and to do eye movement measurements. And we haven't quite hooked it up with EEG yet, but some other people in the world have. And now we can start to do things that are interesting from a cognitive perspective in moving participants. So we can, for example, get participants to encode to stimuli in front of them and then turn them, 90 or 180 degrees around. And all of a sudden it opens new questions, such as which are the spatial frames that participants are using for keeping things in their memory, when there's no longer one possible spatial frame, which is the case when you just sit down and the computer screen is in front of you. Something on the left will always be on the left. Something on the right is always on the right. Once you start turning and moving, something might be encoded to your left, but after you turn to the left, it might be to your right in the world. And so it really starts to open interesting new things to address by getting the agent in a kind of more acting sense, and kind of a behaving agent rather than a passive observer of some computer task that we program. So, yeah, those are just two examples, I think, where methods and question and kind of
I would definitely stick on the second one, and for instance, in terms of language development, studying the perception of isolated syllables is one thing, but with the advances that we recently made with the EEG techniques, we can also study speech perception and language emergence during real life interactions between infants and parents. And this is methodologically sound that has been recently developed or made more robust. So this will offer new ways to study language development. So yeah, definitely this is valuable.
Yeah, this is something that I also wanted to ask to have your insights about. You all presented works with multimodal recording techniques, recording from different indices, not only EEG, MEG, but speech, stomach, many index. And how do you see the future of the methods for integrating these way of this, because we capture phenomenon at a different time scale, and how do you see the future of method that should integrate all of these index?
I mean, at least it's clear, I think, that we need to start measuring way more than just the brain, right? And it kind of makes sense. Yeah, the brain is contained inside the body and inside a behaving agent. And so it's moving, but there's also all these internal signals, eye movements, what have you. But indeed, it raises an interesting question. We can maybe measure all these things individually with, specific devices that are made to do EMG or made to measure body rotation or made to measure the gut or what have you. But how are we going to get them all into the same recording, and then how are we going to make sense of it, right? Because the heartbeat might be locked to the phase of the gut, and the microsaccades might be locked to the phase of the heartbeat, and then the EEG signal is locked to that, and so everything is going to be embedded inside each other at some point, and that's super fascinating to uncover. But to make sense of is a whole other ball game, right? It's definitely gonna make our science more complex, more realistic, and perhaps more fun. But it's definitely gonna add complexity to what we're studying. Yeah.
I don't have nothing to say about that. I have a brain, so I can only integrate small indices.
Yeah, no, nothing to add either.
Okay, thank you very much. I think we are close to 5:32. So I think we're going to close this session. Thank you again, Catherine, Clément, Freek. Thank you so much for presenting us your work today, and thank you for being with us at CuttingGardens. I think we should call this a day, and I can leave the stage to Maximilien. No, he's trying to say something. Sorry, he's in front of me. I'm trying to guess. And
thank you so much, everybody. Thank you, our three speakers. It's really a great pleasure to have you all and your insights during these sessions. The day is still long for some people on the other side of the ocean. The day is already quite late for others on the other side of the world. Please all keep doing what you like to do with EEG, MEG data. We'll see you tomorrow. And yeah, for us, we call it a day. We're going to have a very nice drink at the welcome cocktail. And more tomorrow. Also, probably some visits around. We'll have a few more surprises beyond the science here. Thank you all, and see you tomorrow. This is it. Cheers.